right. Here, this problem I stole from James Elder in order to teach 2011. And I made up the slides, and then I thought they were good in here, so we stuck them in here. All right, so here's the problem. We're trying to find the prefix averages. What does that mean? The input is going to be a bunch of numbers. So the inputs, I think, are the orange, right? And what we're going to try to compute is for each prefix. And what's a prefix? It's a subset of the numbers that are continuous and at the beginning, right? So for each prefix, we want to know the sum, the average. And I've had various versions of these slides that have been wrong, and now I'm starting to see that I think actually in my 2011 slides I changed these, so maybe I should copy them off. Here's a little, it's the 0 that confuses things, right? I mean, here I get in the picture, I got this is indexed by 1, but here I'm indexing by 0, so that's a little bit of a bug, right? But I kind of got it right that I'm dividing by I plus 1. Anyway, the point is, right, for each I want to know the average up to I, right? So we try to write code to do that, and how we could do it is, well, we got all these numbers, there's all these A values we want to compute, so that's what we're going to do. It's going to have I be from 0 to I guess we only go up to n minus 1, right? And we're going to now in here compute this guy. And so how do we compute it? Is, well, you need to calculate the sum, right? The sum from 0 up until I. That gives us our S. And then we take our S and we divide it by the right number. All right? Everybody good with this algorithm? Yeah? All right. Does it work? Yeah, it works. Some of the indexing is funny, but yeah. All right. So now let's do the running time of this. Right? The purpose is, yeah?
What's the prefix of this image? So is that from 1 to 4? What's the prefix?
The prefix is we're going from 0 to I. So here this is not indexed at 0, but we're going from 0 to I.
So from 1 to 7?
Well, that's the entire list. So if I is, so let's look at this green line, right? This green line is taking this orange line, this orange line, and this orange line and averaging them, right? And you see this green line kind of looks like the average of those orange lines, right? And then this green line is bigger because it's the average of these 4 lines, right? Everybody understand the problem?
Sir, in that diagram, what represents the array A and what represents the array X?
X is orange, A is green. Right? So the green is the average of all previous oranges up to our current orange. Right? So we had, I mean, it's not a bad thing to do in life, right? Think about we're going to have a lot of tests in this course, not just 3 or 4 or 5. We're going to have a lot of tests, and the orange are the tests. And after you complete the test, what do you want to know? You want to know what's my average so far, right? So here, this is your average so far. Now, you bombed this test, so your average came down. Right? Everybody following that? And how do we do it? This is probably the way you'll do it. You finish the test, you go home, you add up all the test marks you've had so far up until your current one, and you divide by the number of tests you had so far, and you tell me that's my average. Right? Everybody good? All right. So it was a fine algorithm, and the reason James Elder was doing this is because he was giving an example of running time. All right? So what's the running time? Is let's say which of these lines of code is working the hardest, right? is being executed the most. And this guy here is inside both loops, right? So it's getting executed the most. How many times is it getting executed?
N squared.
N squared, right? And now, where is it n squared? Well, it's 1 plus 2 plus 3, right? Because as it gets bigger, we're adding bigger and bigger sum. But we still know that that's n squared. Right, everybody got that? And now I'm going to say the running time's is n squared because, I don't know, however many lines there are that's doing that, it's a constant and I don't care. And the other stuff is all smaller stuff, right? So the running time is order n squared, right? Okay, right? Other lines don't matter. Time n squared, right? So now, can anybody come up with a better algorithm? Can you do this in linear time? I want to do this in linear time. I don't want to take n squared time, right? And so here I'm using loop invariance as a motivator, right? You might not know how to do it in linear time, but you know about loop invariance, and you know I've been pushing you about loop invariance. So let's think about what the loop invariance is, right? After I've gone around I times, my loop invariant will say I have the answers for them up so far, right? That's one loop invariant. But there's another loop invariant that I could stick in. What's my other loop invariant? What else do I know?
Number of elements so far?
Yeah, I know the numbers. What else do I know?
That the previous prefix has been calculated.
Yeah, but that's not, well, that's here. So we did that already,
Yeah.
right?
I know.
So a new thing, yeah?
Sum.
The sum, right? The fact is, I know the sum because just before I divided, I knew the sum, right? Everybody good with that? All right, so if I add this as a new loop invariant, right, I'm ready to start my new loop. So I often do this when I come up with algorithms, right? I'm trying to improve my algorithm. I have an algorithm that works already. So now I might think, okay, how can I strengthen my loop invariant? What do I need to do this step. To help me do this step, give me everything that could be helpful. So I'm going to write down here everything that I know already. And one of the things that I know is I know the previous sum. So now, how do I make progress? Well, here's something that we're going to be talking about later. People panic, they don't know how to do the steps. And one of the things I'm going to emphasize in the later examples is, well, you have to do two things. You have to make progress, and you have to maintain the loop invariant. So the one advice is, well, what's your measure of progress? I. You got to make progress. How do you make progress? All you have to do to make progress is make I bigger. Right? Why? Because I is your measure of progress. So right there, we just made progress. Right? But what went wrong is our loop invariant is no longer true. Right? Right? So to make our loop invariant true, we have to start calculating things. All right? How do we maintain the second loop invariant? Right? The second loop invariant, where is it? Here. Is we need to know the sum. Right? Well, the loop invariant tells me, oh, see, this is definitely slides from before I fixed the bug. All right? So I'm going to, when I go home, I'll try to remember to copy them over from 1090. Not in 1090. What's the course? 2011. All right? So here, you see how I'm doing it wrong. Right? Because S is the sum up to this number. So if I want to make progress, what number should I be adding in? Right? I need to be adding in the next one.
No, we have I equals I.
Oh, you are. See, he's on it. All right, so we did do it. We did do it. Here, we increased I, so we are adding on the next number, right? I think actually what I did in this slide is I just made it so it wasn't so confusing. All right, you must admit this is a little confusing. All right, so everybody good with that? We maintain that loop invariant. And then how do we maintain the first loop invariant? Right, we just have to do that. Right? And And how do we establish the loop invariant? Right? How do we get the postcondition? Right? We're all good. Everybody following this? And now, what's the running time? Right? Those are all our hardest things, but they only get executed n times. Right? So we're doing order n. Everybody good with that? Was that a good example of telling you how you can use loop invariants to help us come up with better algorithms. Right? Everybody good? All right, what are we doing now?